This video is on solid revolution, and I have this yellow region right here, and I'm going to revolve it about the y-axis, and then I want to find the volume of the solid revolution. And we're going to use both the shell method and then also the disk method to show that they will get the same answer. So here's the yellow region right here, and it's bounded above by the graph y equal to 0.5x squared plus 2, and then it's bounded on the right side by the line x equal to 4, and then here we're on the left side by the y-axis, and then down here by the x-axis. So now I'm going to revolve this region right here about the y-axis. And here's what the solid of revolution looks like. And so the solid of revolution that we want is the part that's without the what's called the paraboloid up here. And so what I'm going to do is I'm going to use what's called the shell method to find the volume of the solid of revolution. And so here's what the cylindrical shells look like. So these are called cylindrical shells. And so what we're going to do is we're going to divide this solid of revolution right here without the paraboloid into n number of shells, and then find the volume of each shell and then add the volumes together, and that will give us an approximate volume for the solid of revolution. So this is shell number 1, and the inner shell, the shell starts at 0 and it goes to 0.5 right here. So the average radius is 0.25, and then the height of the shell would be, we would use this equation right here, which is the graph of this curve, and then plugged in 0.25 and we get 2.03125. The thickness of the shell is 0.5. The formula for a cylindrical shell, the volume, is 2 pi times the average radius times the height times the thickness. And so in this case we get 1.595. Here's shell number 2. The inner radius is 0.5 and then the outer radius is 1. And so the average radius is 0.75. To get the height for the shell, we would use this equation right here, and then in the place of x, we replace it with 0.75, and that will give us 2.28125. And again, the thickness here is 0.5, so the volume will be 5.375. And then here's shell number 3. The inner radius is 1, the outer radius is 1.5, so the average radius is 1.25. And then the height of the shell, we would use the 1.25 and then plugged it in here, and that will give us 2.78125. And then the thickness again is 0.5, since we're making all thickness the same here. And so the volume for this shell is 10.922. And then here is shell number 4, and the volume is 19.414. And here is shell number 5, volume is 32.03. Volume, shell number 6, volume is 49.946. Shell number 7, volume is 74.343. And then shell number 8, volume is 117.81. And now let's add the volumes of the A shells together, and this is what we get. So here are the volumes of the 8 shells. And so altogether is about 311. And so the volume of this solid of revolution that we want without the paraboloid is approximately 311. And so what I have just done is just divide this solid right here into A shells, cylindrical shells. But what if we want to divide it into many shells? And then so that we can get the exact volume of this solid of revolution right here. And so this is what an ith shell would look like. And so let's go find the volume of this ith shell. And so notice that the radius of the shell ranges from 0 to 4. And so what I'm going to do is I'm going to divide the interval from 0 to 4 into n sub-intervals. And so let's call the first one here x sub 0, x sub 1, x sub 2, x sub 3, x sub 4. And then we get to what's called the ith sub-interval. And then we get all the way over here to 4, which is x sub n. And so right here, if this is the ith shell, then right here would be x sub I minus 1, and then right here would be x sub I. And so if we just divide this solid of revolution right here without the paraboloid into 4 shells, then the thickness of each shell would be 1. But if we divide the solid of revolution into 40 shells, then the thickness of each shell would be 0.1. And so in this case, if this is x sub I minus 1, this is x sub I, then the thickness of this shell would be x sub I minus 1. And so let's denote the thickness of each shell as delta x. So delta x would be the thickness of each shell. And now let's find the volume of this ith shell. And so once again, the distance from here to here is x sub I minus 1. The distance from here to here is x sub I. And so if we do x sub I minus x sub I minus 1 dividing by 2, then we get the value right in the middle. And so let's call it x sub I star. So x sub I star is the average radius of the ith shell. So x sub I star would be from here to here. The height of the shell would be the distance from the x-axis up to the curve. But the curve is f of x equal to 0.5 x squared plus 2. So this curve right here is f of x equal to 0.5 x squared plus 2. And right here, this is x sub I star, and so the distance from the x-axis to the curve will be f of x sub I star, which is the height of this shell. And so the height of the ith shell will be f of x sub I star, which is equal to 0.5 times x sub I star squared plus 2. And so the thickness of the shell is delta x. And the volume of a cylindrical shell is 2 pi times the average radius times the height times the thickness. And so in this case we'll get 2 pi times x sub I star, 0.5 times x sub I star squared plus 2. And then the thickness is delta x. And so this is the volume of this ith shell. Now, if we divide this solid of revolution right here into n shells, then the volumes of the n shells would look like this. This is volume of shell number 1, volume of shell number 2, and then this is volume of the nth shell. And then using summation notation, then we would have I from 1 to n with the expression 2 pi times x by star, which is the average radius, and then times the height of the ith shell, which is 0.5, times x by star squared plus 2, and then times the thickness of the ith shell. So the volume of this solid of revolution right here without the paraboloid is approximately this sum. And then at the beginning of the video we saw that it should be approximately 311. And then if we want the exact volume, then we have to divide this solid of revolution here into an infinite number of shells. And so meaning let n run to infinity. And then we get a limit quantity like this. And if this, once again, if this limit right here, if this limit quantity right here exists, then we would define it as the integral from 0 to 4. And then the expression here is 2 pi, and then here we get x is 0.5x squared plus 2, and then dx. And then the 0 to 4 here is 0 to 4. And then simplify, we get the inside here, we get 0.5x to the third plus 2x. And then evaluate this definite integral right here. And then here we get the integral for x, 0.5x to the third is x to the fourth over 8. And then the integral for 2x is x squared. Evaluating from 0 to 4, we get 96 pi, which is 301.59. And then once again, at the beginning of the video, we saw that the volume of the 8 shells that I simulated was of the sum of the volumes of those 8 shells was 311, but here we get 301, so it's very close. So the exact answer is 96 pi. And now let's find the volume of the solid of revolution using the disk method, and we will show that we'll get the same answer. To find the volume of this solid of revolution right here without the paraboloid, what we can do is find the volume of this paraboloid and then subtract from the cylinder that's outside here. And so let's find the volume of this paraboloid right here. So notice that the paraboloid ranges right here, this is 2 up to 10. And so I'm going to divide the interval from 2 to 10 into n sub-intervals. So 2 to 10, and let's call the first one y sub 0, y sub 1, and then we'll get to what's called the ith sub-interval, and then when we get up to 10, this is y sub n. And so this disk right here, this is the ith disk. Now the distance from the x-axis up to the bottom of the disk, of this ith disk, will be y sub I minus 1. And the distance from the x-axis up to the top of the disk would be y sub I. And so the thickness of this disk will be, of the ith disk, will be y sub I minus 1. If we divide this paraboloid right here into 8 disks or 8 slices, then the thickness of each slice will be 1. Now if we divide this paraboloid right here into 80 slices, then the thickness of each slice will be 0.1. And so in general, the thickness of each slice will be 8 over n, and let's denote it as delta y. And so delta y would be 8 over n. And so now let's find the volume of this ith disk. But before we do the volume find the volume of this ith disk, the axis of evolution is the y-axis, and so we need to solve this equation right here for x in terms of y. And so we have the equation y equal to 0.5x squared plus 2. Subtract 2 from both sides, and we get 0.5x squared equal to y minus 2. Multiply both sides by 2, and then we get x squared equal to 2y minus 4. And now take the square root of both sides. We get x equal to the square root of 2y minus 4. And then let's rewrite this equation right here as the function g of y equal to the square root of 2y minus 4. And so this function right here, the graph, this part right here. And so once again, the distance from the x-axis to the bottom of this ith disk is y sub I minus 1. And then the distance from the x-axis up to the top of this disk is y sub I. So right here, this is y sub I. And so the distance from the y-axis to the graph would be g of y sub I. But g of y is the square root of 2y minus 4. And so g of y sub I would be the square root of 2y sub I minus 4. And so that's what the distance from the y-axis to the graph. But this is the radius of this ith disk. And so the radius of this ith disk will be the square root of 2y sub I minus 4. So the volume of this ith disk would be pi times square the radius squared times the height, which is pi times the square root of 2y sub I minus 4 squared. And then recall that the thickness, the height of the disk, in this case is the thickness of this disk, which is delta y. And once again, if we want the exact volume for this paraboloid, then we need to divide it into an infinite number of slices, meaning allow n to run to infinity. And so we let n approach infinity, and then we get this limit quantity right here. And then when the limit here exists, we find it as the definite integral from 2 to 10, 2 to 10. And then here we get pi, and then the square root of 2y minus 4 squared, and then dy. And then simplify here, we get 2y minus 4. And then evaluate this definite integral right here. It will come out 64 pi. So the volume of the paraboloid is 64 pi. Now the volume of the cylinder outside, the height is 10, the radius is 4. So the volume of the outer cylinder would be pi times radius squared times height, which is 160 pi. And so the volume of the solid without the paraboloid would be 160 pi minus 64 pi, which is 96 pi. And a few moments ago, when we found that the volume using the shell method, we also got 96 pi. And so that's so the exact answer is 96 pi. That's the end of the video.